And
hello and welcome everyone to another Data Science DC talk. I'm going to be your host, Chris Smith. I am one of the co-organizers here with Data Science DC. And Data Community DC, we're under the umbrella of which has different organizations all devoted to data science here. So if it's your first time here, welcome. And if you participate in social media, these are links right here. Okay, so here's our contact info. So you see me there, Chris at datacommunitydc.org, and we here have Tommy. Jeff is currently stuck at the passport agency, but he would definitely join us, and he gave me the opportunity to actually MC this event. So thank you so much to that. And of course, Maria, she's another data community co-organizer as well. All right, so with every meeting, we like to establish a code of conduct. Essentially, we are trying to provide a respectful and harassment-free community, so we can learn and grow among our peers here in the data science community. So if anybody feels that you've been harassed or just feels offended in that matter, please contact any one of us at the co-organizers. You can contact me directly at chris@datacommunitydc, or you can ping me in the chat as well. And we also want to start off with our Data Community DC diversity statement. We are essentially, we want to make sure we invite speakers who represent us, a very inclusive culture and very diverse. So we encourage everyone, all data community professionals out there to, be a part of the organization. And I'd like to thank our sponsors. Without them, we wouldn't have this Zoom and other things like in past events we've had, before, in the before COVID, we were actually being able to meet in universities and other office spaces, and they would provide us with the food, empanadas and pizzas and things of that nature. So we definitely appreciate our sponsors for letting us keep this going. Okay, and here we have some upcoming events and announcements. September's, wow, I can't believe September's was about that. We're at the halfway mark. Data Week DC is coming up, which is a great event. It's kind of like the annual send-off of the year. We have a talk coming up in October, and our talk is going to be on an academic talk on language services. So, and if you'd like to join us on Slack, there's our link right there, and please subscribe to our YouTube channel. And if anybody has any community announcements, such as job announcements, internships, please just add them to the Zoom, just chat them on the Zoom. That way then everyone can find them. Okay, all right. So now I'm gonna just kick it off to you, Jim. So we can get it started. You just want to give a brief introduction about yourself and start your presentation.
Thanks, Chris. Thanks a million. My name is Jim Dowling, and my uncle lives in DC. So if anybody's calling in from Kelly's Irish Bar downtown, please ask for Tony Dowling and say I said hello. But yeah, all joking aside, I like DC. But I'm going to talk today about the feature store, and I'm going to talk about our open source feature store called Hopsworks. And in particular, I'm going to talk about, and the slides, by the way, are in the chat if you're curious. I pasted a link to the slides in the chat. And I'm going to talk about how feature store fits into the end-to-end, or what we call MLOps lifecycle. So how do you do end-to-end MLOps? And you can do it on our platform, and we'll talk a little bit about that as well. And please ask questions in the chat. I can stop and interrupt my train of thought, no problem. Okay, so what is a feature store and how do we get there? Now, this is a data science meetup, and often data sciences require feature stores in enterprise environments, particularly. because they have difficulty getting at the data that's hoarded by the data analysts and the data analytics teams. And the data engineers have been told by management, well, you need to get your data in the hands of the data scientists because your data is on the data warehouse, the data lake, it's on the Kafka event bus. And ML engineers, whose job it is to put models in production, have to take whatever is produced by the data scientists, and they will also need to get some state from the feature store to make predictions with models, because models typically in an enterprise environment, they're not these stateless things. We don't, if we send an image to a model to do some classification, the image is very rich in information. But in an enterprise environment where maybe I just have a user ID, a user clicked on something, I need to have some state, some background state to look up about the user, the history of the user. You know, what interactions have they had with the organization? What products have they bought in recent time? What's their credit score? All that state or context about the user's interaction with the enterprise will come from the feature store. So ML engineers need to interact with the feature store to get that state to build these, what we call feature vectors, to make models work in production. So connect the models to the data. Okay, so we have some more links here. Right, so that's the feature store, but what about this MLOps? So what does MLOps mean to the different personalities involved? And data engineers think they know what it is. It's orchestrated pipelines. That's a typical way in which they automate the movement of data from one system to another. So it could be ELT or ETL. Data scientists are not really new. They're quite new at this game of operationalizing their code. And you know, there is a movement out there to have notebooks as jobs. People like Netflix have pushed that. We actually support that as well. And other companies like Databricks are moving that way as well, and Microsoft. And then we have the ML engineers who really want to you know, put models in production, and that typically means Dockerizing or containerizing, running that maybe on a Kubernetes cluster, and then being able to monitor that in production to make sure that you know that the thing is working as expected. So automation is the keyword for MLOps, and the different actors are at kind of different levels of maturity and how to put this all together. Now, the thing to note here is that they need to work together, these three different actors, right? So the data engineers, the data scientists, and the ML engineers, and maybe at smaller organizations, you have one person who plays all of these roles. But in larger organizations, they need to collaborate because you want to automate the production of models, the training of models, the deployment and the monitoring of models, and automate as much as you can to reduce the burden on people who are operating these and putting them in production. So what I'm going to talk a bit about is this. This is the end-to-end lifecycle. You have raw input data in the left. I'm going to actually scribble a bit on the screen, so I hope that you don't mind. So we have raw data coming in from the enterprise on the left. We need to turn that data into features. So the features, as you know, are the kind of the signals that we use, compressed signals of information that we're going to use to make predictions with. And we'll store those features as pre-computed features in the feature store. From there, we can create training data to train models, validate models, serve those models online or offline. And then for the online models, we need to monitor them in production. So I'm going to talk about this life cycle, and I'm going to intersperse it with code examples from our platform, and I'll show you the platform as well as I move along. And please feel free to interrupt me and ask questions. Okay, so let's start at the beginning, feature engineering. And how do you do feature engineering? So traditionally, feature engineering involves taking data in an enterprise setting. This might be in a data warehouse, or it might be on a data lake, or it might be on a message bus like Kafka or Kinesis. And then taking that data and extracting it from the source. Often you're computing aggregates because you want to have a signal that's very compressed. So, you know, if I'm trying to find out make predictions about setting the price of a hotel room, I might read all of the bookings for a month and compress that into something called a load factor for the room over a month. So I don't need to have 30 rows of data about the bookings for that particular month. I can just have one value, which is the load factor, which is this compressed signal or feature. So that's aggregation, and often we'll transform these values as well because, you know, we want numerical stability when we're training models. So we might normalize numerical features, and then categorical features will one-hot encode, and this is all pretty straightforward to many people here. And many of you will know that you can do a lot of this in SQL, so people do that, and dbt is a popular tool in the data engineering community, excuse me, to orchestrate SQL jobs. But more and more people are using Python and Spark, so PySpark or ScalaSpark, because of the flexibility. You have more libraries for computing richer types of features, things like embeddings, graph embeddings, word embeddings, very difficult to do in SQL. And you have different support for a wider set of sources. So you're not restricted to having your database as the input and the output, which you are typically in SQL, but in general purpose languages like Python and frameworks like Spark, you can read data from pretty much any source, join it together, and output your data. And the commonality here is that the data between SQL and then Python and Spark is that the data comes out in tabular format, typically. So we'll have a table as the output with pre-engineered features in SQL, and we'll have data frames coming out from Spark and Python that will be pandas data frames. And they can be materialized to different places. Okay, so now I'm going to get a little bit complex, right? This is a complex slide to take in. We have our raw data, the enterprise data here, and that data is going to go into the feature store. So we're going to do this feature engineering that we called it. Now you'll notice that transformations have moved out of this box here. So I'm just using the term aggregations. You have, of course, extraction, but also data validation. And transformations you can see are happening after the feature store here. So between the feature store and when we create training data, so we're going to take features from the feature store and reuse them. So we're going to say, okay, I want this feature and this feature and this feature. That's one of the points of the feature store is we can reuse features that are computed in these pipelines over here. And when we get out training data, now this is where data scientists typically say, well, I want to one-hot encode this particular categorical feature, and I want to maybe shift this numerical feature or normalize it, and they need to have some control over the transformation. So that's typically why one of the reasons that happens here. The other main reason is for exploratory data analysis. So if your data in the feature store is stored one-hot encoded or normalized, it's very hard for data scientists to actually browse that data and understand it. And I'll give some examples in a minute. I'll just show you how you can do that in our platform. So the feature store is really a catalog as well for features. So one of the challenges you have here is that if you're applying transformations after the feature store, before you're creating the training data, or when you're creating the training data, and you're also serving these models online, so you have some input data coming in here, and we'll also have data features coming to the feature store, so pre-computed features. So how many times have you used your credit card in the last month? Those pieces of information will need to transform again. So that number of times you used your credit card in the last month, it could be normalized. So where does that transformation function that normalizes that numerical feature get executed? Well, it needs to be executed before we send the feature vector to the model. So typically, in our case, we're going to look at how we do that with Python functions. You can define a Python transformation function and apply it consistently between training and serving. In our platform, you can also do this with pipelines like scikit-learn preprocessing pipelines, TF or Keras preprocessing pipelines, and PyTorch preprocessing pipelines, but I'll skip over those today. They involve saving the pipelines to the model repository and then reading them up in your serving infrastructure and applying it yourself. You have to do a bit of work yourself. Okay, let's move on. So this is kind of what we're going to talk about, this particular workflow, the raw data going to the feature store, and then training models from the feature store, and then serving models and using the feature store to build these feature vectors. So let's get started. So this is very simple. It's a DC or a data science meetup. We have features. In our case, we group features together. So we saw earlier that SQL outputs tables and Python and Spark typically output data frames. This is the output here. We call it a feature group. And think of it as being a table or a data frame. You'll note that there is a primary key associated with the feature group, and it can be a multi-part primary key, and we'll need that if we want to retrieve the values of these features in our online applications. So I might, for example, want to retrieve the credit card, the number of times the credit card was used for user ID 2, and I'll get these features and all of the features for that user with the primary key value 2. So let's look at the code for this in our platform. So we have, here's an example of firstly connecting to the feature store. So we're going to connect to the feature store. If you run the code you can run it from any Python or Spark environment. So you can run it from Databricks, or we can run it from from Colab or SageMaker. Once you connect it to the platform, you have this feature store object. You can then create a feature group. This is the table containing the features. They have a version. So for MLOps, it's very important that you version things, pretty much everything. In this case, we're versioning the schema of this particular feature group or table. Because if you have, for example, over time, this feature group, you're going to change the implementations of features. Maybe you have an embedding and you want a new implementation of the embedding, you go from BERT to BERTA. Then what you'll need to do is go from version 1 to version 2, because you can't mix that old embedding with the new embedding. So you'll need to create a new one, and then you'll need to backfill that new feature group. And similarly, if we drop features from this feature group or do any schema breaking change, we'll need to increment the version number. This is called the sales feature group, by the way. We then have a primary key that we can specify for it. And we're doing that because this feature group will be both online and offline. And then if we want to enable what we call point-in-time joins for this, and I won't go into that in too much detail, we can specify the feature or column in the feature group that supports point-in-time joins. Let's see if we have questions. Are different versions of the table stored, or is it keep the latest? That's a very good question. So if we, I'm basically defining the abstraction, the feature group. But when the feature group is accessed and read, there's two downstream clients. One is the when we create training data, and you can see them here implicitly, right? So when we're creating the training data, here we're going to store the historical value of features. So the features that are used for, say, historical. So if we gave the example of credit card usage, and we said how many times I used my credit card in the last week, well, for the previous year, there'll be 52 different values of that. And the 52 different values of that feature will be stored in something called the offline feature store. So I've been trying to give this talk without using the terms online and offline too much, but I'll introduce them now. And in the online feature store, we store the latest value of the feature. So the online feature store will have the latest for the most recent month. How many times have you used your credit card? So the historical one, or the offline feature store, we can use to create training data, because we can go back in time and then look at the number of transactions you've had in the credit card for this period of time, and then match it up with the other feature values at those points in time, and that will create all the training data for us. Okay, so let me, before so that's the API for creating it. I'm going to just show you what it looks like, just to make it a bit more realistic. And if you're curious and you want to play along, if you go to hopsworks.ai, it's free to register. You can register with a Google account. You'll get a demo cluster, and you can play along with what I'm doing here, actually. Now, if you really want you get a demo account on the demo cluster. It's really just a playground. But if you do want to use it, you do need to connect. This is a managed version of our platform in AWS and Azure. You do need to connect on AWS, cross account role you need to create in your AWS account. And then when we create clusters, we'll create them inside your account. So when you create a cluster, and there is Terraform for this if you're curious. I don't want to type in stuff here, but the data will be stored in an S3 bucket in your account. And the same is true for Azure. It's in Azure Blob Storage. And it's using a tenant ID in Azure to basically create the cluster in your Azure account. So this is a cluster I have here running. This one has I put in a GPU node and a couple of workers. We can do feature engineering in the platform or outside it. And I did open up the port so that we can access it externally. And I can just show you, like I was running this one, I think, just beforehand. I pip installed our library HSFS, and we can just run this here. So this is basically me connecting to the feature store from a Python client outside the platform. So there I'm connected, and then we can issue a query to basically look for one of these feature groups. So here I'm actually getting a reference to a feature group. I'm doing very simple exploratory data analysis. I just want to have a look at the top 5 rows. And this is actually going to the historical feature store. I can say the online one if I want to get the data from that one, if it's there. And this is another example, slightly different one. I'm going to write data to the feature store. So in this case, what I'm doing is I'm seeing if this feature group exists, and if it does, I'll just leave it there. But if it doesn't exist, I'm going to download some data into a pandas data frame. So we can see we've got a data frame here, and this is containing the clean data available at this location. And then I'm creating a feature group, and you can see I have a two-part primary key. We're going to store the data in the offline feature store in a format called Hoodie, which is Parquet data with metadata on top of it. It'll be stored in the online and offline feature store, and we're going to compute statistics on it. So in fact, let me see what's been an issue here. I must have checked something here. Oh, I didn't. I don't have a valid scope. Okay, so I need to create a new API key to do that. We can do that, but I'll do that in a second. So I need to log in again. Okay, so let's have a look at these feature groups before we kind of move any further. This is the feature group that was created there. It didn't populate the data because I didn't have an API key to actually write to it. I didn't have the correct scope, but we can have a look at one of these. So let's have a look at this feature group here. You can see there's 3 features. There's a primary key. If we have something called expectations and tags, we can have them there, and we can have a quick preview of the data. We can look at any statistics computed over the features. So when we write the data, the feature store by default will compute these statistics, and we can see the distribution of feature values. And this is all EDA. So this is the thing I was saying before, that if we had normalized, for example, this team budget, it mightn't be so easy to understand for a data scientist. So typically we don't. And then you can preview data. So you can search as well for features, and we can tag them and so on. So here we can get a quick look at the data, and we can search for team and see, well, there's a bunch of feature groups here, and there's a bunch of individual features that match on that. Okay, let's go back. So this is the feature group, and this is kind of the basic use of the basic reusable unit in the platform. And what we can do, as we saw already, we can read up a data frame and then insert it into the feature group, and then it'll write the data in there, and it'll write to both online and offline because we had online enabled true. And you can do this in a streaming app. You don't have to do this just in a batch app. It doesn't have to be a Python app or a Spark app. It can be even a Spark streaming app. And we do have early Flink support at the moment to do this in even lower latency. So in Spark streaming, you have data frames as well, and you're basically calling insert stream on our feature group to insert that Spark data frame. And Spark streaming has very good support for computing aggregates over data indexed by time. Okay, if you're paying attention, when I was going through the feature groups, we saw something called data validation. So one thing we can do is when we write data to a feature group, we can have declarative rules defining what is valid data for individual features. So these rules that belong to an expectation, we can say, for example, a feature has a minimum value of 0. And if that constraint is broken, we'll get a warning. We can also have an error, so that will basically stop writing the data if the maximum value of the feature exceeds 1 million. So one of the nice things about Hoodie as a framework when we're writing data is it has ACID properties. So the update will either succeed or it won't succeed, and we won't have partially written data that we need to clean up afterwards if we get, for example, a validation error. So what we do is we define these expectations. We can attach them to feature groups, and then when we insert data, these validation rules get executed. Let's see if we have a question here. Can we have great expectations? So currently we're supporting DQ. So we have one of the DQ developers working with us. Great expectations is really nice. You can use it yourself. We just don't have it built into the platform. So you can do your feature engineering in Python, use great expectations, and everything works fine. We haven't added support for it yet. We're looking at it. We've looked at it, and we decided to go with DQ because it has better support for Spark currently. That situation may have changed from when we made that decision a year ago. So that's how we get data in. Now, there is another use case that we have. You might call them virtual tables or external tables, where we don't actually copy the data in. You may have a Redshift data warehouse or a Snowflake data warehouse, and you still want to make those features available because the feature store should be this central place where all your features are available. You can do that. You can create what we call an on-demand feature group. And in this case, I'm creating a connector to Snowflake. And then this is a database in Snowflake, and I can issue any SQL query inside here, which will return basically this set of features. It's a data frame. And what will happen is then these features will become available just like any other features. We can set statistics config to be true so that the statistics will become available on the platform as well. And what happens when you run this line here is it will actually run a Spark job that will read the data up using this SQL query into Spark, and then it will compute the statistics, write them to the feature store, and then it'll shut down. But let's have a quick look at the difference between these feature groups in the platform. So let's go back here. Hope you can see this. So yeah, we can see a little moniker, this green one, that means the feature is online and offline. And this one, this black means it's just offline. And we can see here that this is an on-demand feature group. It's telling me it is. So this data is coming from this connector here. It's not stored in the platform, it's stored outside of it. And we can still have statistics over that data, as you can see here. Now you can define storage connectors pretty easily here. I think this is storage connector here. So if I want to set one up for Snowflake, I can just fill in the API key here, and you can use IAM roles if you're in AWS instead of keys as well. Okay. So let's have a look at how these basic features. We said they're reusable. So what we want to do is use them to create training data to train models with. And we want to decouple the pipelines that fill up these feature groups, because these feature groups are mutable. They get updated the whole time, you know, and with Hoodie, we get a history of the updates. We can, you know, go back in time to see what the data looked at that time. But what a training data set is a snapshot from these feature groups at a particular point in time. And we also want to be able to do things like transform the features before we create the training data set, and also filter out data. Maybe we want to train a model only on people who live in DC, for example, based on the features. So what we need to do is be able to join features together from different feature groups, and we need to be able to maybe transform them and filter them. So let's have a look at and obviously we're assuming here now supervised machine learning. So training data sets, we assume we have a label, and then we do have a primary key as well. And the primary key will be used to join these features together. So let's have a look at this. And before I show you how we join these features together from the feature group in our API, I'm going to show you how we do the transformation. So this is a simple Python function called dateString to timestamp. It takes in a stringified date and returns a date as an integer. And it's a very simple transformation. And you basically put this in a Python, in a file inside a Python module. And then we can use this transformation when we want to create the training data set. We can say, apply this transformation to this particular feature. So this is the transformation function here. This is the representation of it here. Again, it's versioned. When you're doing MLOps, everything should be versioned. And then to join features together, what we're doing is we have this sales feature group, and we want to select all of the features from it. And we're going to join it with a different feature group called exogenous. And we're going to join it with 2 features from there. Now, what the query planner does internally is it looks for the largest overlapping set of join keys or primary keys. So in this case, we have the maybe the product that's being sold or the store ID as a common join key. And then this query object, you can get a pandas or a Spark data frame and train models on it directly. But when we create a train data set, we can apply these transformation functions, and we can apply filters. And we can say, materialize the data to, for example, a bucket in S3. We can also have a connector in here and say, write this to this bucket in S3 or this container in Azure Data Lake storage, and store the data as TF record file format, which is native to TensorFlow. So you're going to train my model in TensorFlow. Or you could have CSV or NumPy files or PyTorch. So when you run this last line, what it'll actually do is you can run this code in Python or Spark, but it will actually run a Spark job. So if in the Python client, it will run a Spark job on our platform, which will do the join. So even if you have very large volumes of data, the Python client won't blow up because it'll run on our platform. And if you're running out in Databricks, it'll run natively in Databricks. It's reading up the feature groups as different data frames. It's joining together, applying the filters, and then transforming the data into the file format that you want and saving it to disk. So, and it's applying the transformation functions. So it's going to, for this particular feature called sales TS, it's going to apply that transformation function to it. Okay. So once you train, so now we've created a training data set, we assume we're training a model, and I'm going to skip over the training of a model. I think most people are familiar with frameworks like scikit-learn and TensorFlow and PyTorch. But let's have a look. So there's two types of models we'll typically get. Analytical models used to create reports often, and we batch applications that read up the model, read up some data. They can go to the feature store in these feature groups to read data without labels, and then score that data and write it out somewhere. And then we're more interested now about operational models, because in operational models, we need some serving infrastructure to serve the model, and it's going to go to the feature store to retrieve these historical and contextual feature values. We'll need them to build the feature values. So let's have a quick look at how we do that. So what is the feature vector? The feature vector is basically, it's the exact same columns that we had in the training data set, but we don't have the churn, or so the label in this case, which was called churn week. So we're going to have the same primary keys, it might be more than one, and the same set of features. And when we want to look up a feature vector, we need to supply the primary key. So it's going to be the user ID, the product ID, or maybe some multi-part primary key. We're not using the term entity ID in our platform. If you may have noticed, some feature stores do that. We don't do it because databases don't do it. We don't think there's a need to do it. You can have multi-part primary keys. Implicitly, what we have are foreign keys that we're joining these feature groups together with. And the other thing is that we write to our feature store. We don't use the term ingest because these programs write to the feature store. There's no write amplification in our platform. We're not writing out to somewhere else and then saying, please ingest to the feature store. Okay, so now I want to get into serving. I'm going to retrieve this this particular feature vector, and this is where sort of the magic happens at some level, because we said already the training data set, it's in the feature store, it has the metadata, it knows the set of features, their types and their order, and we know the version of it that was used to train a model. So with this training data set object in our serving infrastructure, so this is just a normal Python serving infrastructure, something like, it could be a Flask server, or it could be Kubeflow model serving. And basically with this TD object, first we connect to our online feature store. That's what this line does. So we'll need to do that. But then after, and that takes only a couple of milliseconds. And then in less than a millisecond, we can get back a Python array with the actual full feature vector. We're passing in here the primary key, and there may be some values that you, excuse me, pass from the application. But the training dataset object knows what transformation functions are applied to what features, and they get applied in here. They get applied transparently to you, and you get back the transformed value. So the library is actually applying the transformations inside this call. So that's basically it. Then that's the end-to-end story. We go from our raw enterprise data, we go to features and feature groups, and these are reusable, immutable sets of features. Trained data sets are these immutable kind of materialized set of features from the feature store, and we use those to train models. And the statistics for our trained data sets can also be used to do model monitoring. We can use it to monitor the live traffic coming into models and compare it with the training data. So the descriptive statistics on the training data to see if there's things like data drift happening in your online model. Now for MLOps, what we can see is that there are dependencies between all of these steps. So you have feature groups, you have derived feature groups, trained data sets, changes in upstream entities cause downstream entities to run. And we'll have two typical pipelines here in an MLOps environment. We have one pipeline writing to the feature store called the feature pipeline. And then we have another pipeline creating the models called the training pipeline. And then finally you have the model monitoring. So these cover our three personas at the beginning, the data engineer, the data scientist, and the ML engineer. So maybe you missed it, but do you specify feature columns in a feature group? Or it's just that every column is not a primary key and a label column. So when you create a feature group, you can create it directly from the data frame, and it will infer the types of the values. You do specify the primary key, and the primary key are just a subset of columns from the feature group, and every other column is a feature column. So we don't need to specify whether that feature column is a categorical feature or a numerical feature, an embedding, or whatever it is. The label column is only specified when you create the trained data set. They don't exist as such until you create a trained data set, because the feature groups are just features, and what is a feature in one model could be a label in another model. So they're only you only specify those when you create training data sets. Thanks. Okay, and then so who does all of these steps? Well, data engineers, as we said, typically do the first steps, data scientists, the training pipelines, and ML engineers, the serving. And data architects do the governance. So the kind of, when you do move to MLOps, some of the triggers that we have here is that, you know, code gets committed and maybe feature pipelines will typically run at a cadence, maybe every hour or whenever new data arrives at the enterprise system, or maybe it's a streaming app that when events arrive in your Kafka topic or Kinesis, then it computes new features and writes into the feature store. The training pipelines can run when you know, if new code is committed or if new data arrives in the feature store. So new data arrives in the feature group, we need to create a new train data set. And we can also have time triggers, of course. And there's many different orchestration frameworks you can use to do this. On our platform, we have Airflow, but GitHub Actions and Jenkins, we have users who use those as well. And then model monitoring, there's a bunch, it depends on your model serving infrastructure. I'll talk about our example in a second. So we do have Airflow internally to do this orchestration of the steps, but there's many different ways of doing orchestration of these steps. So the bigger picture for at least for our platform is that the data comes in from here, from the data engineering, it goes out to the data science frameworks, and then the data from the feature store goes out to serve models, and then you may have a metadata framework to manage the data throughout its lifecycle, like Collation or Informatica or Calibra. And this is a little bit of repetition. So the feature pipeline is pulling the data in from the enterprise data store and writing it to the feature store. One thing that we do have, and if you go through the example, we have another framework called Maggie, and there's a talk linked down here, which does, and this is part of MLOps, is you want to actually scale out your training. So you want to, if you want to find good hyperparameters, maybe you want to parallelize the search for them because you have a lot of resources. And the same goes for training. If you have a lot of resources, a lot of GPUs, parallelizing it, data parallel training will make your training go faster. So Maggie is a way, a framework to do that, where you can just write the training logic once and reuse it between hyperparameter tuning and distributed training. So that's a part of it. And then the other part, the serving infrastructure, and this is part of our framework again, we're using Kubeflow model serving. So the way Kubeflow model serving integrates into an application is the application makes a call on Kubeflow model serving. So it makes a call either on the REST endpoint or the result gRPC endpoint. And then Kubeflow itself, internally, it has a Python class that you can plug in, call it transformer, and that will connect to the feature store. And then when a request comes in, and we see the request number 1 coming in, it will then, in the pre-process step, it will get the features back from the feature store, and that's number 3. And then it will then build up the request that it sends to the model, makes a prediction, and then the result gets sent back. And what we've added to this is that we also log the request to Kafka. So we have Kafka as part of the platform, and that means we get live traffic coming into Kafka about how the model is running in production. So what we can do with this, and we had a talk at Spark Summit this year, or the Data AI Summit, I should say. You can find out more about it. Is we do have a templated Spark streaming job, which will compute all of these statistics for you, and then you can write them out to wherever you want to write out. So these are classic kind of outliers, drift statistics that can help you identify when your model might need retraining, for example. Now, the other thing you can do when your prediction logs are in Kafka, which is really powerful, is that you can understand the performance of your model by doing things like interactive queries to debug the model to see, hey, what was that query that caused the problem? Maybe you want to look at KPIs of the models and is this model meeting its KPIs, or do we have problems with it? And then obviously things, just operational issues like the performance of the serving infrastructure in terms of latency, and then being able to store this historical data for auditing. And then of course, because you have these predictions coming in, It is possible to, if you also have your outcomes arriving, so your system that's running live is maybe predicting whether a user will buy this particular item. Well, either the user will buy it or the user won't. That outcome, you may learn that. You can add it to your feature store and create new training data. And this is kind of the virtuous data flywheel. Now, I do have an example, but I won't have time to go through it because I talk way too much. It's available here online, and I'll talk about it briefly, and I can just show you the notes. It's basically using a huge volume of data, 40 terabytes of data, to train a generative adversarial network for money laundering, predicting money laundering. There is a webinar tomorrow about it, if you're curious. And we're replacing rules-based anti-money laundering on the left with using machine learning models to predict whether financial transactions are suspicious of money laundering. So basically your data comes in from the bank, from different sources, and it's stored in a feature store, and from there we can train a model, we can store the model, and then it can retrieve the features as it needs them when a financial transaction comes in. So if you look through the use case itself, you'll see some examples that we have a feature group related to the financial transactions themselves, so the money payments. And the person involved, that's called a party, whether it's an individual or organization. And then we computed graph embeddings from those transactions. And we also have a list of the transactions that were suspected, or called alerts, suspected of money laundering. And we use those to evaluate the model, in fact, because in this case, we're using the GAN to train on the transactions that are not suspected of money laundering. So we're doing anomaly detection here. Okay, but I won't go into this in any detail. And this is kind of how the whole thing lines up, that you basically start at the raw data and you convert the features, and then we can deploy the model and so on. So I'll just show you the notebooks, and I won't have time to go through them, but let's have a quick look here. This is the platform again. I did have a Jupyter Notebooks. No, it's on this particular project here. So the Jupyter Notebook server running here. So if you check out this code, you'll see there's 9 notebooks in total, and they walk you through from creating feature groups to creating the training data for the embeddings, computing the embeddings, and then adding those embeddings to a full trained data set. They're going to train your model, and we're using Maggie again for parallelizing the hyperparameter tuning as well as the distributed training. Okay, so that's basically it, and I think I've no more slides to do it. Go. Let's have a quick look. Yeah, and this is kind of what you get with the whole platform if you're curious. You know, we have, so this is kind of internally inside it. You can pick and choose whatever you want. If you just want to use the feature store, that's fine. But the platform does have support for Flink, Spark Streaming, Spark, and Python for feature engineering. There is a feature store. You can do model training on any Python library with GPUs. There's Jupyter Notebooks, Jupyter Hub, and then there's a model repository and Kubeflow model serving that I didn't show you, but I'll just show you briefly for those who are curious. Let's go back here, and I'm going to go back. There's a data science UI for this. I'm just going to go over here to that. So this was the AML example I ran earlier. We have there's support for experiments in here as well, and with TensorBoard. So we can see here, this is an experiment I ran, and if we look at the you've hyperparameter tuning here as well, so you can see there's multiple runs of experiments, and then we have the model registry with the models here that I trained, and then we've got model serving here. This is model is running currently, and then you can see in this case I actually have 1 GPU in this cluster. Excuse me. Okay, I think that's it. Let's go to the last slide. So the platform's open source, and we are a company behind it. And there is actually a feature store summit next month, if you're curious, on the 12th and 13th of October. And we have some really great, if you're interested in feature stores, I'll just show you this. There's speakers from, I think if we see the speakers, we have basically all the main makers of feature stores from, you know, AWS, Bosch, Databricks, Berkeley, Equatio, but then we have, of course, the big ones like Salesforce and Uber and Spotify and so on. So that's that, and I think there's a couple of questions, Chris. I hope we can. I can take them there. The slides are available. They're in the link actually. So someone wrote it up there. And then there'll be a YouTube video out soon.
If so if they scroll up, they'll definitely get the link. But
Yeah, it's at the top of the chat.
yeah. Okay. Oh yeah, and the video will be up. Tommy will give us usually with 48 hours we have the video up for today's.
Yeah, I'll try and get it up tonight since we recorded right at the beginning. There shouldn't be any editing really required.
Okay, great.
Well, I guess if there's no more questions, we can probably adjourn for the night. Thank you, Jim, for a great presentation for our audience here, and thank you everyone for coming.
Thanks for having me.
All right, thank you very much, Jim. Appreciated it.
Thanks, guys. All the best.
All right.
Bye.
Bye all.